This is 3.4, concavity and the second derivative test. And so when we took a derivative, what did that find?
The slope of the tangent.
The slope of the tangent line. That told me my function was either increasing or decreasing. And so now when we're talking about concavity, we're going to talk about something else. And so it's going to be very similar, but I'm going to talk about these slopes. So what do you think the slope is there?
Negative.
Negative what?
1, 2, negative 4.
I'm going to go negative, like steeper, like -3, -4, something like that. And then what do you think my slope is there? -2, -1, something like that. And then what's my slope there? 0. And then my slope here? Okay, and then my slope here?
6 or 7.
More than that, right? And so then what's happening to my slopes?
It's decreasing and increasing.
My slopes are increasing. My slopes are increasing, which means concave up. When the slopes are increasing, that means concave up. And vice versa. And so if my slope's here, this would be a big positive, and then a smaller positive, and then a smaller positive, and then 0, and then a negative, and then a bigger negative. And so when my slopes decrease, I have concave down. And so that's how we're actually talking about concavity. Concavity is actually the slopes of the slopes, because when I talked about increasing and decreasing, that's when f prime was positive or negative. So now I'm talking about a slope of a slope, which means I'm talking about the second derivative. All right. And so now I'm talking about a second derivative. So f double prime is greater than 0 when f is concave up. And f double prime is less than 0 when f is concave down. Just like we did for increasing intervals and decreasing intervals, now we're going to talk about intervals that are concave up and concave down. So our function here is 6 over x squared plus 3. So what derivative do I need to get to when I'm talking about concavity?
Second derivative.
I need to talk about the second derivative. All right. So we first need to take a first derivative, though. And what ruler do we want to use? Quotient rule. So let's do it. So what's the derivative of the top? 0. And then times the bottom. I don't feel like writing it because it's going to be 0. And then what? Minus the derivative of the bottom, which is 2x times the top of 6, all over the bottom squared. And so now I have x squared plus 3 squared. And so when we simplify that, what would we get? Negative 12x over the quantity x squared plus 3 squared. And so there's my first derivative. So now I need to take a second derivative. So f double prime of x. So what's the derivative of my numerator? Negative 12. And then times the bottom, which is x squared plus 3 quantity squared. And then what? Minus. Now when I take the derivative of the bottom, what comes out front? A 2. And then I have x squared plus 3 to the power of 1. And then a 2x pops out by the chain rule. And then times the top of negative 12x. And then it's all over the bottom squared. So now I have x squared plus 3 squared squared, which is really to the power of 4. What you should notice here is that every term has an x squared plus 3 quantity in it. Okay? And so what I'm going to do is I'm going to kind of think about distributing, dividing here. And so what happens is that each power is reduced by how much? 1. And so now this is going to go bye-bye. This is going to go to a power of 1. And then this goes to a power of 3. All right, so that's what I would suggest doing first when we're doing our algebra. And so now what would I do with this negative 12? I would distribute that guy in. And so now I'd have negative 12x squared. And then minus 36. And then I have negative 2 times 2x times negative 12x. So that would become what? Positive 48x squared. All over the quantity of x squared plus 3 cubed. And so now I would simplify it up a little bit more. And so then how many x squareds do I end up having? Positive 36x squareds. All right, and then what could I factor out when I'm starting to work with it? I'd factor out a 36. And so now I have 36 times the quantity of x squared minus 1 over x squared plus 3 cubed. All right, and so there's my second derivative. And so now I take that and I set it equal to what? 0, because I'm trying to figure out when my concavity is up and down. All right, and so then I'm going to set that equal to 0, and what do I get? X equals 1 and x equals -1. And so just like we did in our first derivative test, now I'm going to make a sign chart using a second derivative. And so I would notate which derivative I'm working with. So this derivative sign chart is f double prime. And so I would notate it because now I don't want you to get them mixed up. And so now let's pick something left of -1, like what? -2. And so when I substituted -2 right here, this would become what? The top would be positive. The bottom's always going to be what? Positive. So then I would end up having a positive. And so then pick something between -1 and 1, like 0. And so then what do I get up top? A negative. The bottom's always going to be positive, so then I get a negative. And then pick something more than 1, like 2. So then I get a what again? A positive. And so now let's answer our question. And so when am I concave up? When am I concave up? From -infinity to -1, and from what? 1 to infinity. Now, the reason behind it is because why? F double prime is what? Greater than 0. So now let's talk about concave down. So when are we concave down? From -1 to 1. Because why? F double prime is less than 0. So like when we took a first derivative and we set it equals 0, or when we found out when the first derivative did not exist, we found critical numbers. So if we set our second derivative equal to 0, or when we find our second derivative does not exist, this is called a possible point of inflection. All right? Because a point of inflection actually has to change concavity. So just like your pre-calc days, how do we get a point of inflection in pre-calc? It was a what? It was a switch in concavity. It was a change in concavity. So F double prime actually has to change signs to be a point of inflection. All right? So it's a possible point of inflection when our second derivative is 0 or doesn't exist.
Determine the points of inflection and discuss the concavity of the graph. F of x is equal to 4 or x to the 4th minus 4x cubed.
All right, fantastic. So if I need to talk about points of inflection and concavity, I need to get to what derivative? Second derivative. So let's do a first derivative. So f prime would equal what? 4x cubed minus 12x squared. All right, and so then we need to get to the second derivative. And so f double prime would equal what? 12x squared minus 24x. And so now we're going to take that and we're going to set it equal to 0. But before we do that, I would f something up. So what would I factor out? 12x. And then we're left with x minus 2. And we're going to set that equal to 0. And so then we get what? X equals 0 and x equals 2. So what do we call those? We call them possible points of inflection. All right. I had a past student. She called them p-poise, and so I kind of like to call them p-poise now too. And so they're possible points of inflection. All right. So they're not poise. They're p-poise. They're possible. All right. Those are our possible points of inflection. But now we're going to make our what? Our sign chart. And so I'm going to notate it by f double prime. So we're going to have 0 and 2. So let's pick something left of 0, like what? So this would be negative. This would be negative. So now we have a, and so now we pick something in between 0 and 2, like what? 1. And so now I get a what? Positive and a negative, which makes it a negative. And then pick something right of 2, like, so then it'd get a what again? Positive. All right. And so, do I have points of inflection at these two x values? Yes, I do. So I have points of inflection at 0 comma something. How would I get that something?
Let's put it back in.
Back substitute that into the original, and so what would be my y value? 0. And then I'd substitute in 2, and so 2 to the fourth is 16 minus 32, which is negative 16. So I have points of inflection because concavity changed sign. And so what we really need to say is that f double prime changed sign. That's my reasoning. All right, so on this one, we're going to find relative extrema, but we're going to use the second derivative test. We're going to actually use the second derivative test to find relative extrema. And our function here is negative 5x to the fifth plus 5x cubed. Where do you find relative extremas at? At critical numbers. How do we get critical numbers? Take a derivative, set equals 0. So let's do it. So we're going to find f prime. And so f prime would equal what? And so now I'm going to set that equal to 0 eventually, but I'm going to factor something out first. I'm going to factor out a negative 15x squared. And then I'm left with x squared minus 1. And when I set that equal to 0, I get 3 critical values, 3 critical numbers. And so what would those critical numbers be? X equals 0, and x equals negative 1, and x equals 1. And so my stuff before, I would actually make a sign chart from right here. Does everybody follow me? I'd make a sign chart, and I'd use my first derivative test. And honestly, that would be a really good way to do this one. However, because I'm talking about concavity, I'm going to go a different way, and then I'm going to freestyle one with you. Nice. All right? And so anyway, but honestly, I would make a sign chart right here, okay? But I'm making an easy one here to make sure we actually know what the second derivative test is. So I'm going to get to my second derivative. So I'm going to look here, and I'm going to take a second derivative. So f double prime is equal to what? Negative 60x cubed, and then plus 30x. All right. And so if I were to simplify this one, I would factor out like a negative 30x. And then I'd be left with a 2x squared. What was that? Minus 1? Minus 1. And I don't need to set that equal to 0 because I don't need to find my p-poise. Because critical numbers are where we have relatives. Okay. And so what I want to try to find is my concavity at these critical numbers. I want to find my concavity at those critical numbers. So what I'm going to find is f double prime of negative 1 and f double prime of 0 and f double prime of 1. So now we're going to take our critical number and see if the second derivative is positive or negative. So if I substitute in negative 1 right here, this would turn out what? Positive. This would turn out what? Positive. So a positive times a positive is a positive. So f double prime of negative 1 is greater than 0, which means it's what? Positive, which means it's going to look like that, which makes at negative 1 a relative what?
Minimum.
A minimum. So I have a relative minimum at negative 1 comma something. And how do I get that something? I substitute it back in. So when I substitute it back in, this would become what?
Negative times negative is positive.
So 3 and then minus 5. So that would be what? Negative 2. So I have a relative minimum at negative 1, negative 2. Now we're going to do the same thing for f double prime of 0. Again, 0 is a critical number. So if I substitute in 0 right here, this would become what? 0. So 0 times pretty much anything would be what? 0. And so f double prime is equal to 0 right there, which makes it a what? A possible point of inflection, because when my second derivative is equal to 0 is a possible point of inflection. All right? We'd actually have to figure out if my f double prime changes sign for it to be a point of inflection. So now we're going to substitute in my critical number of 1 into my second derivative. So this one would be what? Negative. This one would be what? Positive, which makes it what? Negative. So now that one's less than 0, which shows your hand like that. So that would be concave down at that critical number. So what did that make it? That makes a relative max. So it's a relative max at 1 comma something. And so we substitute it back in. And so we get a relative max at what? 1 comma 2. So when we look at the graph, this should totally make sense to us. So we have a critical number by setting our first derivative equal to what? 0. And so we have these slopes equaling 0. And so then we need to find the concavity. So if it's concave up and I have a slope of 0, I have a relative min. If I am concave down when my slope is 0, I have a relative max. And then if it's 0, it's probably going to be a what? A point of inflection. And this one was a point of inflection because it went from concave down to concave up. So this one is for Miss Walker. All right. So let's say I have f of 6 is equal to 7. And then let's say I have f prime of 6 is equal to 0. And then let's say I have f double prime of 6 is equal to negative 7. What do we know is happening at 6, 7?
It's a critical number.
So it's a critical number. How did we know it was a critical number?
Derivative equals 0.
Because my derivatives equals 0. But it's also something more than a critical number. What is it?
Changes from positive to negative, so it's relative max.
Relative minimum because it's concave.
My f double prime is negative, which means it does what? It's concave down. So it's concave down at a horizontal tangent line, because that's what that says. So 6, 7 is actually a what here? A relative max. Because my first derivative is equal to 0, and my second derivative was negative. So that made 6, 7 a relative max. All right, so when we're talking derivatives of derivatives, that actually means what? Concavity. All right, so a derivative is a what? A slope. And so if concavity, that's really a slope of a slope. All right, and if some people like to look at them with this little like chart thing, that would be totally good. And so the way that you can actually like think about the chart is when f prime is greater than 0, that means f is increasing. When f prime is less than 0, that means f is decreasing. When f double prime is less than 0, that means what? Concave down. All right. When f prime is equal to 0, that means what? It's at a critical number. And what happens at critical numbers? We have extrema. We have relative extremas. All right. And so anyway, if you like looking at a chart like this, that's for you. All right. So we got a little bit of problems right here. So we got page 195, numbers 1 through 11 odd, 22 through 26 even, and 37 through 43 odd.